Hello again. Today I will show you how to deal with the free damp vibration of the multi-degree of freedom system. I mean, we will be speaking about how the damped system, multi-degree of freedom system, vibrate without the excitation. I mean, it's a free damped vibration, and it will be in the case of the multi-degree of freedom systems. Okay, and the general form of the multi-degree of freedom system governing equation is as follows. I mean, here we have the inertia force, like always, inertia matrix times acceleration, time the influence of damping, I mean the stiffness, I mean the damping matrix times the velocity vector, and plus k times y, I mean the vector of the restoring force, and everything will be equal to 0 because we are speaking about the free vibration, I mean without the excitation. Okay, and in most cases, I mean in general case, it's really difficult to solve, to make some efficient analysis of such a system, but we can consider some simplified case. I mean, we'll introduce some extra assumption where the damping matrix will be expressed by the linear combination of the inertia matrix and the stiffness matrix. The name of that thing, it's a proportional damping. It's a proportional damping where the stiffness matrix is expressed as a linear combination of the inertia and the stiffness. Damping, it's a linear combination of inertia and stiffness. Okay, let's put our assumption to our governing equation. It will be inertia matrix times y dot plus alpha times inertia plus beta times stiffness times y dot plus k times y equals 0. For the more efficient analysis, I will divide everything by the mass. I mean, for the inertia matrix, we have to remember that in the case of the matrix algebra, the order of the operation has matter. That is why I have to take the left side product. And if we take such a product with the invert inertia matrix, we will get the y vector as a result of that product. Here we have the alpha times unit matrix. It's important because here we have some matrix expression in the parentheses. I mean, if we want to make the proper sum of the scalar thing and the matrix, we need the unit matrix to get the same dimension of the particular component, and plus minus m to the minus 1 times k times y equals 0. I will introduce, according to the analysis of the single degree of freedom system, I will introduce W square matrix, which will be, let's say, some equivalent of the omega 0 square. It isn't the matrix which is composed of the omega 0 square, but the determinant of the omega square minus omega square times I equals 0 will give us the particular values of the natural frequency. It means that it's a matrix which indicates the vibrational properties of our system. Okay, let's use our assumption, I mean our substitution, and as a result we will get that it's a alpha I times, plus beta w square y dot plus w square times y equals 0. And again, due to the analysis of the single degree of freedom, we will predict that the general solution of the homogeneous equation will be expressed as a product of some function which give us the damping effect, I mean some exponentially decreasing function, and times z of t, or I will use also the z without t, but it will be the same, which give us the oscillating properties of our system. I mean, similarly like we did in the case of the solution for undamped vibration of the multi-degree of freedom system, or in the case of the single degree of freedom system, I will predict the solution in such a form, but the difference is in that part that we are assuming that that thing, it's real number, okay? In that case, it will be minus ht. And the oscillating properties, due to the imaginary unit of r, are hidden here. I mean, it's hidden above the z of t or z. I mean the under. Okay, and what do we have to do next? Of course, like always, we have to take two derivatives, because in the next step we would like to put everything inside our governing equation. I mean, as a first derivative, we have the minus he minus ht times z as a derivative of the first term times element without the derivative, plus first element without the derivative times z dot. I mean, the second term will be differentiate, and next step we have to compute the second derivative, and it's as follows. I mean, due to the first term, we have the h square, positive h square times that decreasing term times z minus e minus ht times z dot. The same if we are talking about that component, I mean minus e minus ht times z dot, and plus plus e minus ht z double dot as an effect of the differentiation of the second term of that product. Okay, let's put everything to our governing equation. I mean, let's put particular derivatives to our to that equation. And also I take the common factor in the form of the e minus ht. Okay, I mean, I will take that thing against the parentheses. Okay, let's put the numbers. I mean, due to the last term, we have z double dot, I mean that part, plus h squared times z, and what we see here, important thing, look, we have the similar part here and similar part here. I can add that those two components, and here we have minus 2h z dot. Let's put the second element. Let's put the second element, and it will be connected with that thing. I mean the plus alpha I plus beta w squared times that part, that equation, that expression, minus h times z plus z dot without the damping term, and it will be the last part, last term, it will be the contribution of the restoring forces component. I mean, it will be w times z, because we have to put only the y, and it's a product of the damping component, decreasing component times z, which is here, and we have to close the parentheses, and everything will be equal to 0. We know, like we did last time, that if we want to find the condition where such a product will be 0, we have to consider situation where that first term will be 0 or that term will be 0. Of course, it's not possible to get 0 for every single value of time. That is why we have to consider where that part will be 0. And because we are trying to get situation where our governing equation, let's say, fundamental equation or characteristic polynomial will be similar to the problem on undamped vibration, I will divide my my equation to two components. One component will be connected only with the second and zeroth derivative, like it was in the case of the undamped vibration. I mean, I will take that thing that thing, and that thing. And the second component, second part, will be connected only with the contribution of the damping. I mean, it will be connected only with the z dot. Okay, it means it will be z square. The influence of that thing, it will be minus h alpha I plus beta w square times z, and it will be almost all if we are talking about the z, because here we have also w square times z, and it's all if we are talking about undamped free vibration, let's say, because we see only the combination of the second and the zeroth derivative. And the second part, it will be the contribution of the damping, and it's connected only with that thing and that thing. Let's emphasize that terms, and it will be here. I mean, here we have such a thing. In another parenthesis, we have minus 2h times z dot, and here we have that part. I mean, it's a alpha I plus beta w square, and everything is multiplied by the z dot, and we have to close that big parenthesis, and everything has to be equal 0 due to the previous condition. And look, because we need to deal only with that part, because we know how to solve that problem, we have to force that equation to eliminate that part. How to do that? We have to find the condition where that entire expression will be exactly 0. I mean, I will rewrite that thing. I mean, we have 2h times z dot plus alpha I plus beta omega w square times z dot equals 0. We will take the common factor as a z dot. We know that the z dot cannot be 0 at the for all values of t4 4 times. And here we have the alpha I plus beta w square, and we have to take into account the fact that we are taking the common factor. Remember that if we have such an expression, I mean some scalar thing like our minus 2h in the product with z, we can express such a thing exactly as 2h minus 2h as a times unit matrix times z dot. I mean, if we are taking the common factor, we have to use that formula. We know that the unit matrix is an invariant of the product in the matrix algebra, that it means that it's exactly the same. That is why I will add that thing, and here we have, oh, maybe in that form, minus 2h times I. Exactly the same I mean the unit matrix which was considered here, or which is visible here. Okay, and it's 0. And again, we have the simple condition where that expression will be 0, because here we have that the alpha minus 2h times I plus beta w square is 0. We can divide everything by beta because it's a scalar factor. It means that we have the beta, and we will change the order. I mean the 2h minus alpha over beta, and here we have the result. And look what we have as a result. We have exactly the same matrix which could be considered if we are talking about undamped free vibration, because the w square is given by only by the inertia matrix. I mean the invert inertia matrix times stiffness matrix. And if we consider undamped vibration, we are able to determine the eigenfrequencies, I mean the natural frequencies of that system. We know that such an expression can be, due to the eigenvalues, can be expressed as the omega 0 square with the indicator I. And look, because we are looking for the condition, we are looking for the damping coefficient where such an equation will be true, we have to consider the set, I mean the sequence of the values h. It means that if we will solve such an eigenvalue problem, then we will get that beta times omega 0 I square will be 2hi minus alpha, and as a result we have that hi is a alpha plus beta times omega 0 I square over 2 due to the eigenvalues, natural frequencies of the undamped free vibration of that system. I mean free vibration of the system without damping. I mean here we see the influence of the proportional damping. Okay, and now there isn't anything like that in our fundamental or characteristic polynomial. It means that next we can consider our problem without that part, but for the particular values of the h. Okay, I mean for that values. I will make some rearrangement before the further computation, and I will show you what will be the final result. Okay, let's put something more, because look, due to that condition, we see that alpha I plus beta omega w square can be expressed as minus 2h times I mean due to that equation. I mean from that equation, from that part, we directly get that it will be 2h times I is alpha I plus beta omega w square. I mean instead of that component we can put such a component. Okay, what we'll get as a result, I have to look at our previous equation. I mean we have the z double dot plus h square z minus h, but this time we will replace that term with 2h times I, and it will be times, everything will be multiplied by z, and we have to add also w square times z. Is everything good? Yes, it should be. I mean here we have that component, and everything is equal to 0. What we can do next, we can deal with that part, because we see that it's a z double dot plus h square times z minus 2h times z, because I times z it's again z, of course, 2h square, because it's a contribution of that product, plus w square times z equals 0, and it will be, as we see, z double dot minus h square times z plus wh times z equals 0. And again, we are able to express the w square times z as natural frequency, I mean the omega 0 square I times z, but only for the values of the eigenfrequencies. It means also for the values of the h. I mean, if I will put, instead of w square z, if I put the product with the natural frequency, I have to put that minus h squared times z will be exactly for the values indicates for z, okay? Because it's only the true for that condition, because only for the hi given by that formula connected with the natural frequency it will be true. And that is why we will get as a result that z double dot it's omega 0 square I minus hi square times z equals 0. And now we have the eigenvalues, I mean the omega of our mu, or omega 0, no, sorry, it will be omega h. I mean omega of damped vibration connected with the particular damping coefficient will be given as a difference of the natural frequency of the undamped system minus corresponding damping coefficient. Exactly like it was in the case of the single degree of freedom system, but this time we don't have the one value, we have the sequence of the values. It means that if we are talking about the proportional damping, the equations are exactly the same and the effects are exactly the same. We have to only deal with the sequence of the damped frequencies and damped coefficients. Thank you for your attention. See you next time.